let's get right into it. Today's explainer is all about the invisible infrastructure that powers literally every single video we consume. We're going on a pretty wild journey here, tracing the moving image all the way from basic software commands through some heavy-duty hardware and straight into the mind-bending realm of AI generation. So how exactly is AI completely rewriting the rules of video? That's the big question we're answering today. Think about it. Every time you stream a movie, upload a clip, or watch one of those crazy new generated videos, there is a massive, highly optimized pipeline working furiously behind the scenes. We're going to break down exactly how that works and look at how artificial intelligence is basically tearing up the traditional rulebook. Here's our roadmap for the explainer. We're starting with a foundational video processing bedrock, then looking at how GPU hardware accelerates things. After that, we'll get into deep video compression, unpack something called spatio-temporal transformers, and finally, look at the cutting edge of generating 4D video. All right, let's start at the absolute bottom, the bedrock of modern video processing. The true foundation of almost all modern video is the massive FFmpeg ecosystem. You've got command line tools like FFmpeg, FFplay, and FFprobe for handling files. Then you have components like muxers and demuxers, which basically package audio and video together, and deep libraries like libavcodec. This vast open source ecosystem is really the silent workhorse of the internet. It handles the heavy lifting of traditional video processing. But here's the catch. As we push into 4K and 8K resolutions, relying purely on software and your computer's main CPU creates a massive, stuttering bottleneck. So to handle the massive scale of modern media, we have to look under the hood at the physical silicon, specifically accelerating things with GPU hardware. Modern NVIDIA GPUs actually contain dedicated hardware just to solve that CPU bottleneck we just talked about. I'm talking about NVENC for encoding and NVDC for decoding. What's crucial here is that these are physically separate from the GPU's main CUDA cores. They're purpose-built engines designed to process heavy modern codecs, like H.264, HEVC, and the newer AV1, at faster than real-time speeds. And by taking all that load off the main system, they free up the primary cores to do other things, like training the intense AI models we'll be looking at in just a minute. Just process this staggering metric for a second. 8K resolution running at 240 frames per second. With 4 NBNCs on the new NVIDIA Blackwell hardware architecture, that can actually be achieved in real time. The sheer volume of pixels being crunched by this physical hardware is honestly mind-boggling. And it's not just about raw speed either, it's about pristine quality. The NVIDIA Video Codec SDK 13.0 update introduced an ultra-high-quality mode for AV1 encoding. This delivers the exact same gorgeous fidelity as a slow, traditional software encoder, but with roughly 3 times the throughput. Plus, it supports 422 progressive and interlace formats. This specific leap in hardware acceleration is exactly what paved the way for our next major evolution, teaching neural networks to compress video all by themselves. That brings us to deep video compression, the point where AI really starts taking over the whole process. For decades, traditional video coding relied entirely on handcrafted algorithmic prediction and transformation. But in 2019, a massive shift happened. The DVC framework came along and used convolutional neural networks to replace those traditional key operations end to end. That breakthrough completely threw the doors open, leading directly to early attempts at using token-based vision transformers, allowing AI to analyze frames in entirely new ways. But early AI wasn't exactly perfect at this. Consider the traditional neural approaches. Deep residual coding tried to work by simply subtracting temporal information, like aligned frames, and then compressing the leftover residual data. Then you had deep contextual coding, which just bluntly concatenated or glued spatial and temporal context together to build a dependency model. These early methods were pretty inefficient, honestly. They didn't truly understand how space and time interact, which left massive amounts of redundant data on the table. Which leads us to spatiotemporal transformers. To solve that glaring inefficiency, researchers at Disney Research developed a way to fuse space and time together globally, much like a Matryoshka doll. The result of that research is the spatiotemporal cross-covariance transformer, or STXCT. This is a massive breakthrough. Remember how earlier token-based vision transformers chopped images into little squares and instantly bogged down computational power? Well, STXCT is a 3D-based neural module that takes flat 2D features and seamlessly combines them into a joint spatiotemporal feature. It models global correlations across the entire channel with linear complexity. Basically, it sees the whole picture across time, and it does it without melting your GPU. So how does it actually pull this off? It's a really elegant four-step architecture process. First, it aggregates those individual 2D features into a 3D joint feature. Second, a 3D convolution is applied for local spatial temporal mixing. Step 3 is where the magic happens. It uses multi-head attention across the channels to find global correlations. And finally, a 3D feed-forward gate tightly regulates the flow of all that information. By passing data through the specific gate mechanism, the AI is quite literally learning a deeply integrated global spatiotemporal context. It's just incredibly efficient. And that brings us to the final frontier, generating 4D video. Because if AI can perfectly compress the dimensions of space and time by deeply understanding them, the natural next step is for it to generate those dimensions from scratch. Stability AI's rapid generative progression shows a literal explosion of technology. We started with the original SVD model generating just 14 frames of flat video from an image using a deflickering decoder. Then came SV3D_U, suddenly generating 21-frame orbital videos from a single image, and SV3D_P creating 3D video along specific camera paths. And now, SV40 2.0 is pushing out 48 frames. That's 12 frames across 4 different camera views simultaneously for high-fidelity novel view video synthesis. In just a few short years, we went from basic image automation to generating full multi-view synthetics. With that latest May 2025 model, SV40 2.0, it auto-regressively generates 12 frames at a time. But the truly groundbreaking part? It no longer relies on a reference multi-view of the first frame. This drastically reduces those terrible self-occlusion errors you normally see in real-world videos when objects block themselves in motion. From a single, flat, still image, today's AI can hallucinate a perfectly consistent 4D object moving through time and space from multiple angles. It has redefined video from the ground up. Just look at how far we've come in this explainer. We started with basic command line tools. We built massive silicon engines to accelerate those algorithms. We taught neural networks to compress video by understanding the very fabric of space and time. And now they're using that deep understanding to hallucinate 4D reality from a single still pixel. If AI can compress reality flawlessly and generate entirely new dimensions on the fly, you really have to ask yourself, where will this accelerating technology take us next? And what will the word video even mean tomorrow?